So the goal of this talk is to provide a general overview of what's going on in NVMe. It's not really to dive into any details of any specific technical proposal. There are a lot of great presentations both in this track and in other sessions at FMS this year. You can learn more about that. So before we dive into what's technically new, let's take a look at the NVMe landscape. So as late as 2017 and 2018, we had industry analysts questioning whether NVMe would cross the chasm. And really the question there was, is NVMe going to become a mainstream technology, or will NVMe remain relatively niche, or perhaps NVMe just fade away? So here's data from IDC. It shows the enterprise SSD capacity shipments by interface type from 2018 to 2026. At the bottom in green, you see SATA. Above that, we see SAS. Above that in orange, we see SATA. Above that in blue, we see PCIe or NVMe. So basically, virtually all SSDs that ship are NVMe on PCIe. And above that in dark green, we have other interfaces, so things like Ethernet. And what you can see is in 2018, NVMe capacity shipments equaled that of roughly SATA or SAS. In 2019, capacity shipment equaled that of SATA plus SAS. And in 2020, NVMe capacity shipments started to dominate. And if you take a look at this IDC projection, by 2026, NVMe dominates the industry, and pretty much all other interfaces become niche at that point. Now, this was the plan all along when we started NVMe. I never lost hope and believed that all the way through, but it is always surprising when you see that actually really happen. So here's another way to look at the data. This is in units shipments. So when we started NVMe, we wanted to create a unified interface. At that point, we had SATA for client, we had SAS for enterprise, we had a bunch of different interfaces for embedded. Here, we're looking at data provided by Forward Insights, and these are unit shipments over a 9-year interval from 2016 to 2025 versus market segments. So we have enterprise, cloud, and client. And what you can see is that over this 9-year interval, enterprise shipments are projected to grow by almost 2 orders of magnitude, and client and cloud shipments are expected to grow by over an order of magnitude. So NVMe has become the new language of storage. It's now used in everything from cell phones, tablets, laptops, desktops, storage arrays, and warehouse scale data centers. So, up to this point, I've really been talking about, NVMe PCIe SSDs, but it's important to remember that NVMe supports other transports. We support fabrics that support RDMA. We support fabrics that support TCP/IP, and we also support fiber channel. So NVMe is being called the new language of storage because we now see systems being built around NVMe technology as kind of the native underlying storage technology for those systems. So with that introduction to the market, let's take a look at NVMe 2.0. So, when I talk to people about NVMe 2.0, a lot of people expect some, major new feature or some speed bump in NVMe performance. And really, there are some new features in NVMe 2.0, but NVMe 2.0 is all about specification refactoring. We refactored the specifications for 3 reasons. The first one was we wanted to make it easier to use NVMe technology. Previously we had PCIe information sprinkled all through the base spec. If you wanted to build a Fabrics device, you had to go read all of that and try to understand how it relates to your Fabrics attached device. So by refactoring the specifications, you can now pick up the specifications that you care about and build the system you need without going through a bunch of unnecessary information. The second thing we wanted to do was to enable rapid innovation. So, when you innovate in standards, sometimes the standard gets picked off and becomes huge. Sometimes it doesn't, and it sort of fades away. And what we wanted to do is basically create a document architecture where if an innovation doesn't take off, it's in its own document. People can read it if they want to, but it doesn't go in and create complexity in the core documents. So refactoring enabled that. Finally, we wanted to create a structure that was easier to manage from a document management perspective. So we can now edit documents related to specific topics. It's much easier to manage these specifications than it was before. So let's take a look at what the transformation was. So we took the NVMe base specification, which previously covered the base architecture of NVMe, the NVM command set, and PCIe information. We split it up. We moved the base information into a new base spec. We moved the NVM command set information into a NVM command set spec, and we moved all the PCIe information into a PCIe transport specification. We took the NVMe over Fabric specification. We moved the architectural pieces that related to Fabrics into the base specification, and we then took the Fabric's transport definitions and moved them into their own transport specifications. Finally, the NVMe management interface, we largely moved it over unchanged. There were some items that we moved into the base specification, but it largely remained unchanged. So this is the structure of the NVMe 2.0 family of specifications. There are 8 specifications. They were released last June. There's the base specification, which covers the core NVMe architecture. There are 3 command set specifications. There's the NVM command set. This basically describes block storage. It's what most of you probably think about when you think about NVMe, but we also have 2 newer command sets, the NVMe Zoned Namespace command set and the NVM key value command set. We have 3 transport specifications, the NVMe over PCIe transport specification, the NVMe over RDMA transport specification, and the NVMe over TCP transport specifications. So those of you that are awake this early in the morning might be wondering what happened to Fiber Channel. And the Fiber Channel spec is done in T11, not in the NVMe organization. And then finally, we have the management interface specification. So we now have 8 specifications, and they were released last June. So now let's talk about technical activity that's occurred since the release of the NVMe 2.0 family of specifications. So before we get into that, let's just talk about how technical work happens in NVMe. Let's say a company wants to propose a new feature or capability. They'll get together with a bunch of other companies and they'll put together what's called a Technical Proposal Authorization Request, or TPAR. The TPAR is voted on by the NVMe members and the NVMe board. If it passes, that technical work is then authorized to take place. We then developed a technical proposal around that technical work. It both defines technically what needs to be done and it defines all the spec changes. Once that's done, it goes back to a vote by the NVMe members and board, and if it's ratified, it immediately becomes part of the standard, and the technical proposal is available on the NVM Express website. So if you look at what's happened since last June, we've authorized 27 new technical proposals. So this is basically new work that we're doing in NVMe that we've authorized. We've ratified 30 technical proposals. So these are new features and capabilities that are now part of the standard, and you can go download these technical proposals from the website. And we have some of the world's leading storage experts working on NVMe, and a lot of them have incredible skill in writing very precise and detailed specifications. But despite that, issues happen and we have to go and fix errors and provide clarifications. So we've ratified 5 ECNs since June of last year. So in previous, presentations where we spoke about, the state of the NVMe union, what we would focus on is specification release. And that was simple when we had 3 specification releases. But now with 8 specification releases, it's not really possible to do that. In fact, when we talk about the NVMe 2.0 family of specifications, 2.0 really refers to the revision number of the base specification. The other specifications are at other revision levels. And what we anticipate is that these specifications will all evolve at different rates as needed. So basically, the NVMe organization is changing the way that we communicate things from when we're going to release a spec to when are new features that are available. And these features are available through technical proposals that are available as soon as they're ratified. So this slide basically shows the NVMe specification feature roadmap. The dotted red line represents the release of the NVMe 2.0 family of specifications. The green boxes represent ratified features. So we have two major features that have been ratified. The left edge represents the quarter in which it was ratified. The light blue boxes represent features that we anticipate, major new features that we anticipate on ratifying, and the left edge represents when we intend on or anticipate on ratifying those. And the dark blue boxes represent new specifications. So we plan on adding 3 new specifications. I'll briefly cover those later in this talk. So we're going to be growing the number of specifications in NVMe from 8 to 11. Okay, now let's dive into what are some of the new technical features that we've defined. So, what I'd like to do is some of the technical features names don't exactly match the technical proposal name. So what I've done is I've put the technical proposal in the upper right-hand corner. For technical proposals that are ratified, you can go and download those off the NVM Express website. So for like dispersed namespaces, it's associated with TP 4034. You can go download that. That's a ratified technical proposal, and you can read all about it. So before we get into dispersed namespaces, let's do a quick review of the NVMe architecture. The central thing in NVMe is the NVM subsystem. An NVM subsystem consists of controllers and namespaces. Controllers are the things that hosts connect to. So a host connects to a controller. The controller logically implements the NVMe queuing interface. It logically processes NVMe commands, and it logically maintains the state information associated with the host. The other big piece in the NVMe architecture are namespaces. You can think of namespaces are similar to ones in other storage technologies. And it's basically a container of storage, and this is basically what the hosts access when they access NVMe storage. A namespace can be private, which means that it can only be accessed by one controller. So here namespace A and C are private. A is only accessible by controller 1, C by controller 2, and namespaces can be shared. So namespace B is shared, it can be accessed by multiple controllers. So that's background to the NVMe architecture. So up until this point, a namespace had to be fully contained within an NVM subsystem. And what we allow with dispersed namespaces is to have namespaces that can be accessed by controllers in 2 or more NVM subsystems. To ease use of this, we've defined a log page where you can go and query and find out all of the NVMe NVM subsystem NQNs that can access that namespace. We also extended reservations to work on dispersed namespaces, but basically it straddles 2 or more NVM subsystems. So you might be wondering, who cares? Why do I care if it can straddle 2 or more NVM subsystems? So on this slide, I'm going to show 3 applications of dispersed namespace. So all the way on the left, we have data migration. So let's say you have a storage array, it implements NVMe, you've got hosts connected to it, you buy a new storage array, you power it up, you want to migrate the data from the old storage array to the new storage array, you've got some hosts that are connected to the old storage array, you're prototyping some stuff on the new storage array. Dispersed namespace allows the host to access both storage arrays to get access to the data while it's being migrated from the old storage array to the new storage array. Another example is data replication. Let's say you've got an office in Boston and an office in New York. You put a subsystem in Boston, you put a subsystem in New York. You want the hosts in Boston to connect to their local NVM subsystem and the ones in New York to connect to their local subsystem, but you want them to have access to the same data. So with dispersed namespaces, you can now have data replication across these NVM subsystems in an architecturally consistent manner. The final application that I'll describe is high availability systems. So let's say you've got data and you absolutely need to have access to this data all the time. So here you can build a system, an HA system such as the one shown here. You can have 2 hosts, 2 NVM subsystems, with each host connected to each NVM subsystem, and then a dispersed namespaces between the 2 NVM subsystems. So with this system, you can tolerate a host failing. So if host 1 fails, host 2 can pick up the responsibilities. If a link fails, the host can continue to use the other link to access the data. If the NVM subsystem fails, the host can continue accessing the data using the dispersed namespace through the other NVM subsystems, so HA systems. All right, now let's shift gears to NVMe over Fabric's discovery enhancements. So basically what we saw on the roadmap was NVMe over Fabric automated discovery and NVMe over Fabric discovery enhancements. Both of these new features are really applicable only to IP networks. So basically, automated discovery consists of 2 technical proposals, TP 8009, which is automated discovery of NVMe over Fabric's discovery controllers for IP networks, and 8010, NVMe over Fabric discovery, centralized discovery controller. And then the NVMe-oF discovery enhancements is basically TP8016, subsystem-driven zoning with pull registration. So it's a lot of words. Let me try to explain what's going on. So the first new feature is automated discovery of NVMe over Fabric discovery controllers. So before we can talk about what this feature is, let's just kind of review how discovery works in Fabric-detached NVMe devices. So when you take a host and you plug it into an NVMe Fabric, it needs to connect to a discovery service to figure out what storage it can talk to. So a discovery service is basically an NVM subsystem with a discovery controller. And all a discovery controller is, it's basically a simplified NVMe controller that returns discovery log pages. So when you take a host, you plug it into the network, it queries the discovery controller returns a discovery log page. That log page basically contains all of the NQNs of the NVM subsystem that the host can connect to that may have storage that it can use. It also may contain redirections, so you can have other discovery services, and there could be redirections to those other discovery services. So imagine you had a host, you plugged it into a network. There were really two ways previously to configure the host and to figure out how to get to the discovery service. There could be some administrative configuration. Think of you've got a file with IP address or whatever, how to get to the discovery service. Or it could be using some means outside the specification, which is not standard. So what we wanted a mechanism where you can just take a host, plug it in, and it just works. So what we've done is we've leveraged domain name system service discovery, DNS-SD. So with this feature, we've basically exposed the discovery service as another service that's accessible by DNS-SD. You can plug in an NVMe host. It can use DNS-SD, find out the discovery service, connect, and then figure out what storage it can connect to without any pre-configuration or host administration. All right, so we talked about these redirects. Sometimes you want to limit redirects. So what we've done is we've standardized a way to provide a centralized discovery controller. So we've added two architectural elements, a centralized discovery controller. So this is basically a discovery controller that aggregates information, and a direct discovery controller, or DDC. And these are discovery controllers that provide discovery information to the CDC to make it centralized. So we need a way for DDCs to provide their discovery information to CDCs. And there are basically three ways to do that. The first way is that the DDC can connect to the CDC as a host. It can issue a command to the CDC, which causes it to pull discovery information from the DDC and aggregate it together. So that's called a push mechanism. We have a pull mechanism, and in a pull mechanism, the DDC can signal to the CDC that the discovery log information has changed. It can do this using either DNS or a TCP connection, and that will cause the CDC to connect to the DDC and then pull that discovery information to the CDC and aggregate it together. And then finally, we have administrative configuration. So this feature is all about how do you centralize and get a centralized discovery controller where you can connect to one place rather than having to go chase down a bunch of redirects. So we also standardized fabric zoning. So zoning is not new in storage. What zoning means in the context of NVMe is there's now information that the CDC can use so that when a host connects to the CDC, it only gets back the NQNs of the NVM subsystems that it can actually connect to and has storage for it. So we need to define a couple of data structures. A zone is a collection of NVM subsystems and NVMe hosts that can communicate. A zone group is a collection of zones. We've then defined a data structure on the CDC. So there's a zoning database. The zoning database contains a ZoneDB config, which is basically a list of configured zone groups. We also have the ZoneDB active structure, which is a list of active zone groups. So these are the zone groups that are actually enforced by the CDC and filter the requests by the CDC. So you might be wondering, well, why do we need like an active list and a configured list? Can't we just do with one list? And really the rationale here is that the configured list allows us to basically create zone groups and not have them active. You don't have like this like partially baked zone group that you're configuring running around. It allows you to configure it in the ZoneDB config group before you make it active. So with zoning, we have the problem again where DDCs need to pass zoning information to the CDC. So you want to get it in a centralized place. And you can do that again using push and pull mechanisms. They're similar to the mechanisms that I described for the discovery log pages on the previous slide. All right, now let's shift gears and talk about scalable resource management. So let's say you bought a server, you got a bunch of SSDs plugged into the server, you got a bunch of network adapters in the server, you want to turn it into an NVM subsystem. So you basically load some software on it and you're off to the races. Let's say you want to take that underlying server and you want to expose it as multiple NVM subsystems. Now you could do this in a vendor proprietary way, but there's really no standard way to configure and manage this across vendors. So what we've done is in NVMe is we've standardized the notion of exported NVM subsystems. So what that allows you to do is take the resources of an underlying NVM subsystem and export it as you can think of it almost as a virtual NVM subsystem. So on the fabric, it appears as just a regular NVM subsystem that you can connect to and do whatever you want to. So we've standardized admin commands to create and manage exported NVM subsystems. We've added commands to manage exported namespaces, basically moving them to the exported NVM subsystems, and manage ports. We've also added the notion of a allow host list. So associated with each exported NVM subsystem is an allowed host list. So if a host tries to connect to an NVM subsystem and it's not on the allowed host list, the NVM subsystem will prevent the connection. All right, continuing along the theme of NVMe over fabrics, there are two very important identifiers that all NVMe over fabrics hosts need. They need the host NQN and the host ID. The host NQN is the NVMe host NVMe qualified name, and basically the NVM subsystem uses the host NQN to identify the host and to authenticate the host. There's also a host ID. The host ID is a 64-bit or 128-bit number. The NVM subsystem uses the host ID to figure out which controllers in the subsystem are connected to the same host. And you basically need both of these IDs to be an effective NVMe over fabrics host. So let's say you got a server, you plugged it into a network, you boot it up. Well, you need both of these IDs, so you need the administrator to go and configure this. So what we've done is we've standardized a way where you can use the UUID in the system management BIOS to basically create the host NQN and host ID fields. So now you can basically take a server, plug it in, and it can create its own host NQN and host IDs without configuration. So you might be wondering, well, why do I need this? I could just have Linux make up a host NQN and host ID and I'm off to the races. And really the advantage here is that by using this mechanism, you get the same host NQN and host ID in a pre-boot environment as you do in the OS running. Which gets us to the next new big thing, which is booting. So we're introducing a new NVM Express boot specification. This specification will basically detail how do you boot over NVMe over TCP in a standard way. That is the content of the initial boot specification, but our intention is that this is the specification where we'll put all boot-related topics regardless of transport in the future. So this is a new specification for NVMe. All right, now let's talk about copy. We introduced the copy command in NVMe 2.0. The copy command allowed you to copy from one or more contiguous regions to another contiguous region in the same namespace. So since we released the copy command, there's some ambiguity around atomicity. We're in the process of cleaning that up. But the big thing that we're adding to the copy command is cross namespace copy. So what you can now do is copy contiguous regions across namespaces. So, here's an example. Let's say I have namespace A, B, and C. Namespace A contains range 2 and 4, B contains 3, C contains range 1. You can now use you'll be able to use, when this is ratified, the copy command to copy these ranges into a single contiguous range in namespace D. So it now allows cross namespace copies. But there are some restrictions. So the logical block data and metadata format size need to be the same across all the namespaces. The end-to-end data protection type and size must be the same across all the namespaces. And the logical block storage tag mask and storage tag size must be the same across all the namespaces. So that's extensions to copy. Now let's shift gears and talk about computational storage. So computational storage isn't new. People have been talking about it for a while. And it's really been implemented by some vertically integrated companies, but it hasn't seen mass adoption. So NVMe is in the process of creating a standard for computational storage. Our hope is to jumpstart a computational storage ecosystem with the standards. So let me try to kind of outline the benefits that we see in computational storage. I'm going to do that through a database example. So let's say you want to do a database query. So using a traditional system, what you would do is you'd transfer all the data from a bunch of SSDs into memory. You'd process that data with cores on a processor. With computational storage, what you do is you'd break up that query into pieces. You download a piece of that query to each NVMe SSD. The NVMe SSDs would perform the operation locally and then pass up filtered data, which could then be aggregated and respond to the query. So there are a number of benefits that we see in computational storage. The first is that by spreading these operations out across multiple SSDs, it offers the promise of higher performance and reduced latency because you can increase parallelism. The second thing is moving data across PCIe costs power. It costs about 5 picojoule per bit to move a bit of data on PCI Express. And if you need to move all of that storage data from all your SSDs to host memory before you can process it, you're burning a lot of power. So by keeping the data local, computational storage is promising reduced power. Finally, you may not have enough memory bandwidth to cover all the SSDs that you have. And even if you have enough memory bandwidth to cover all the SSDs you have in your processor, the processor may not support all the PCIe interfaces running at max line rate. So by performing the operations locally, it offers the promise of higher performance and reduced latency. So we're going to be introducing a new specification called the Computational Programs command set. It will standardize a framework for computational storage. And what you'll be able to do is basically execute commands on storage data, execute programs on storage data, and these can be fixed function programs, meaning they can be hardwired in the SSD. So think of things as like compression, encryption, hashing, those sort of functions. Or they can be downloaded programs. So we needed a vendor-neutral way of downloading programs to an SSD. So we decided to use eBPF. eBPF is widely used in Linux to run sandboxed programs. It's vendor agnostic, and it's widely supported. There are lots of tools that support eBPF. So let me give you a quick rundown of how this would work. So if you want to execute a program on storage data, you would transfer the storage data to, we can think of as a memory namespace. You would then issue a computational programs command to a computational namespace. It would then read and write the data on the, think of it as memory namespace, executing the program. When it's done, the result will be put back in the memory namespace. Then you could transfer that to the host or transfer it back to persistent data in a NVM namespace. So I went very quickly through that. There are a lot of details that I've skipped and simplified things, but one of the key concepts that I want to drill into is eBPF. So eBPF, you can think of as a simple instruction set. It's a very simple, think of it as kind of a RISC instruction set that operates on byte addressable memory. So we need some byte addressable memory in the NVMe architecture in order to have eBPF operate. And so what we're doing is we're introducing the notion of, you can think of it as a computation, as a memory namespace. So this is byte addressable memory that the computational program will access. Think of it as kind of like host memory for host programs. We're adding this as a command set because there'll be commands that'll operate on this memory namespace. And we are defining, and we're introducing this as an architectural element because, we may find uses for these, quote, memory namespaces in the future. All right. Next thing I'm going to talk about is flexible data placement. So with the introduction of NAND-based SSDs, which have been around forever, the industry's been on a journey of trying to find a way to allow the host and programs to optimize for NAND-based storage, right? That's been the holy grail. And we've been on a journey trying to do this as well within NVMe. So we first did I/O determinism. We followed that by streams. There was a thing called Open Channel, which led to Project Denali. So the industry has been on this journey of trying to find the right way to expose this. And basically the problem's been, and the reason that these schemes haven't really succeeded is that either the scheme didn't provide enough host control to allow you to optimize for the NAND, or it exposed underlying NAND details and controller details, making it very difficult for you to build interoperable solutions. So those solutions provided a lot of control, but it was very difficult to get multi-vendor sourced solutions. So we're now in the process of standardizing flexible data placement. It's a thing that we just started working on the last few months. And the way to think about it is it's going to be an extension to the NVM command set. Programs and hosts that understand FTP will be able to get an advantage by optimizing for the underlying NAND. If you don't understand FTP, you can still run legacy programs and it'll run just fine. So it's an extension to the NVM command set. So look for that in the future. The final feature I'm going to talk about is key per IO. So we've had self-encrypting drives in NVMe forever. And what a self-encrypting drive does is it allows you to provide a key for an LBA range. And sometimes you want finer grain control. So sometimes you want to be able to specify an encryption key for an important file or a storage object on storage. Sometimes you want to be able to specify a key in a read or write operation to make GDPR easier to implement. Being able to specify a key in read and write operations also simplifies cases where you have erasure code or data spread out across multiple devices where you need to erase some data and preserve other data. So what we've done is we've standardized a mechanism for you to specify a key in a read or write operation. But basically, downloading and management of those keys is outside the scope of the NVM Express specification. So we've been working with TCG on specifying a mechanism that can be used with this. We have a liaison agreement in place and we've been working through the details. Although the technical work for this technical proposal in NVMe is completed, we're holding up ratification until the TCG work is done to make sure that the two fully align. And we expect that to happen either later this year or early the following year. So, I provided you with a quick summary of what's going on in the NVMe organization. There's a lot going on. I encourage you to attend many of the other talks. But basically, NVMe technology has succeeded in unifying client, cloud, and enterprise storage around a common architecture. We're seeing people build systems around NVMe as the core architecture for their storage array. And what we saw from the data earlier is that NVMe is expected to dominate the NVM storage marketplace. NVMe 2.0 was all about specification refactoring. There were some new features, but really it was about specification refactoring. Post NVMe 2.0, we're shifting the way that we're speaking about evolution of NVMe from specification releases to new feature releases. Features are released in technical proposals. These technical proposals become part of the NVMe standard as soon as they're ratified, and they're available on the NVM Express website, so you can quickly download those technical proposals and implement them. So since the release of the 2.0 family of specifications about a year ago, we've authorized 27 new technical proposals, we've completed 30 technical proposals, and we've ratified 5 ECNs. So the NVMe organization is doing a huge amount of technical work, and that technical work continues as we move forward. Thank you.